So over last week, we looked at lift and drag in some applications and used the conservation of really momentum and energy to explain, in some sense, what is lift and what is induced drag. And conservation of mass, momentum, energy is going to go throughout the entire course, and so is Navier-Stokes equations. So not sure today, but like either end of today or on Wednesday, we are starting to look into Navier-Stokes equations, starting from very simple scenarios. And today we are going to continue look at lift-induced drag, and also starting to look at the vortices. So basically, we are going to really introduce our next model, next aerodynamic model in the hierarchy, which is a lifting line model. Okay. So first of all, we started with this air cylinder model, right? So basically, a cylinder of air with the diameter being the span of the wing gets pushed downwards, right, behind the airplane. And we said that it is useful in kind of explaining the lift through conservation of momentum and explaining the induced drag through conservation of energy. It also quantitatively predicts how much induced drag there is with some accuracy. And it has several things that are wrong. First of all, the air outside of the cylinder has to move to make way for the cylinder, right? Today we're going to see like how that is going to be remedied by the lifting line theory. And also the air inside the cylinder is not going to be moving at a uniform velocity. Today we are also going to see that is remedied by the lifting line theory. And also the explanation is not satisfactory about why. So that's something not going to be remedied by the lifting line theory, right? The lifting line theory kind of tells you that the flow behind the airplane has some vertical structure, but still it doesn't really explain how the vertical structure is set into motion. So that we're going to really wait till further when we look closer to airfoils for us to be able to explain that. Okay. But the homework actually this week, okay, is going to be exercising this this cylindrical theory. So basically, looking at one of the birds that actually is very remarkable. It flies basically around the globe many times throughout its lifespan, and we're going to look into basically the design of this bird to figure out how much lift it is generating and how much energy it spends over the entire lifetime overcoming induced drag. Okay, and you're going to find out the design of this bird that make it incredibly efficient in how much energy it has to spend over this much distance, which is equivalent to going from the Earth back to going from the Earth to the Moon and back for many times. All right. Okay. So again, this is useful in terms of predicting the induced drag, but like this prediction, this formula, right? Remember, it scales with the lift squared and inversely scales to the square of the span. Actually helps us in making engineering and piloting decisions, right? For example, if you want to efficient airplane, make the span large. And we're going to see if you want to make the induced drag large, you also make the lift large. So, does any of you fly like hang gliders or paragliders or live in areas where a lot of people fly them? No? Or visited the areas where a lot of people fly them? Not really? Okay. Do you know like when people flying like either hang gliders or paragliders, if they want to get down fast, what do? No? Okay, so let's watch the video just to get some experience on like what people do when they want to get down fast. What's happening? Okay. So this is the launch of the hang glider. It's on a boat. The boat speeds up and yeah, the glider comes up. goes higher. So the gliders catch thermals, which is upward going air, right? That's how basically they go up further without any power. And they usually go into shallow circles just so they stay within the upward lifting air. Okay, so now it's a problem. So it's not a fun thermal, it's actually a building thunderstorm. So this guy now looks worried, right? So the primary job he has to do is to get down fast, right? To escape the. Right now he is looking to if he can glide to somewhere else that's not in the uplifting air. But soon he starts to realize this is too big, right, to escape. Okay, so here, let's look at what he actually does, trying to get down fast. What do you think is this guy doing? Yes?
Like going down in cylinders.
Going down in circles, right? So this is also exactly what the paragliders. I mean, if you go to some like a mountainous area where a lot of people go on paragliders, you see a lot of people like doing this when they try to get down faster than, let's say, if they have two people gliding down at the same time, they want to land at the same location. So one person has to go in front of the other, right? So the person who is going in front needs to go down faster than the other. So that's exactly what they do to get down like in front of the other person. So why is this useful in getting down faster? Yes?
Because like the normal for the force is now like pointing inwards, and so it's like that y component is reduced. So yeah, now as opposed to if you were just flying straight with the paraglider, you reduce the component that you're introducing into the y component.
Yeah, so basically you are tilting the lifted direction, right? So why is tilting the lifted direction useful?
It no longer acts against gravity, so now gravity can begin pulling you down.
It no longer acts against the gravity. That's well. If you look at the hang glider, it's not descending in an accelerating way, right? So it is. I mean, the vertical speed is probably higher, but it's not accelerating. So some component of the lift force is still balancing the gravity. So what is making it descending faster? Yes?
When it's at an angle, the lift force is now also at an angle, which is much smaller than the original lift force.
So you're saying the lift force is less than the original lift force, which is actually
Like the vertical component.
yeah, the vertical component actually balances the lift, balances the gravity, right? Because you're still descending at a constant rate. So there is no vertical. I mean, there is horizontal acceleration because it's going in circles, but there is no vertical acceleration, right? Do you agree? So what's your answer? You also raise your hand.
I was just going to say, like, the projected wingspan is significantly decreased, so if there's any, like, rising air, it would also have a smaller effect.
Okay. If you have a rising, so let's think about rising air just as kind of a rising air everywhere, right? It's not just a small patch of rising air. So if you think about Einstein's relativity, right? Being in a big puff of rising air is no different from the air not moving at all, right? So this is and just the change in the coordinate system. So essentially, the fact that you are trying to descend in a rising air is essentially the same as saying you want to descend in a static air with a speed that's faster than the speed of the rising air, right? So basically, you're trying to descend fast. That's all. Okay, anybody else has ideas on why tilting the lift force is useful in getting down? You can think about what we did using this theory, right? The induced drag is proportional to this. Yes?
I was just going to say something about the induced drag, that it was like greater because of the speed.
The induced drag is greater because of what, actually? Well, if you look at speed, it actually goes against the induced drag, right? Here, to go down fast, you want to increase induced drag, right? So that basically the induced drag times velocity is how fast you are dissipating the gravitational energy, right? So basically, when the glider goes down, the gravitational energy feeds into basically the gravity force times the speed of descent needs to balance whatever drag you have times the velocity, right? So the energy of the system is conserved. Again, does tilting the lift force going in circles reminds you of something we just saw in the Top Gun movie? What is Maverick doing when he's tilting, like having the airplane go like that? Yes?
Using a lift force to create like a centrifugal force to turn it.
Yes, he's using lift force to create the centripetal force to turn the airplane, right? And his face goes like, that's because he's experiencing a lot of G's, right? Which means when you tilt the lift force, is the lift force bigger or smaller? It's bigger, right? Basically, if the lift force is tilted like this, yes, we're entering a deep spiral, which normally results in a rapid descent, right? I mean, this is actually intuitively true for people who are flying like hang gliders and paragliders. But aerodynamically, why is that true? It's because when you're tilting the lift force severely, the vertical component of the lift force is now balancing gravity, which means there is also a horizontal component. So the total lift force is multiple times, okay, the weight of the hang glider or the airplane, right? So however many G's Maverick is experiencing, that's how many more times the lift force is in that scenario. In this case, this guy is maybe maximum experiencing 2G or something, but well, now they are doing something else. Like so later on, what I think he was doing was, instead of increasing the induced drag. Okay, anyway, so the deep spiral he's doing basically is intended to multiply the lift force by like a factor of 2, right? So if you multiply your lift force by a factor of 2, how much are you increasing your induced drag? A factor of 4, right? So that's how you get down faster. Okay, right? So that's really what is about going spirals for all of this. And later on, I think he did something even more effective. That's basically climbing out and basically blocking the air. So again, it is increasing the drag, right? Increasing the drag basically makes the glider go down. All right. Any questions on this? So this is parasite drag instead of induced drag. So induced drag doesn't seem to be getting him down fast enough, so he has to be like that. All right. Okay, any questions on this? Okay, anyway, so today we're going to be doing something even more useful. So that's lifting line theory. So the one thing that kind of makes us start to question this air cylinder model is scenarios like this. So if you look at the wake behind an airplane in a real video recording. So this is an airplane with flaps down, going through a cloud. It's maybe not easy to see over here. But what you see is that it's not really the span of the entire airplane that mattered for pushing down the air behind the airplane. But it seems that what matters is the span of the flaps, right? So this makes us question, right, this kind of an air cylinder model with the cylinder being the entire span of the airplane. Because what if the outermost portion of the wing is doing nothing, right? What if it's just sticking out, being like tiny sticks? Then, of course, it shouldn't really be pushing down air. It's the inner portion of the wing that actually provides significant lift that matters. So, essentially, the wake behind an airplane should not just depend on the span, but also depends on the lift distribution along the span. Right, so that's basically leads to our next model. That's the lifting line model. Okay, so let me just state the lifting line model first before we discuss either the consequence or the rationale behind the lifting line model. Okay, and then we're going to first discuss the rationale, discuss actually the consequence of the lifting line model, like how it is useful, and then come back and figure out where the lifting line model comes from. Okay, so you already learned this in Unified, right? So I can go through this relatively quickly as a reminder. So the lifting line model basically says that the flow around an airplane, actually today we are only going to look at far behind the airplane, but like the lifting line model actually describes the entire flow around an airplane with the summation of three components. The first component is simple, the free stream, right? As if there is no airplane, there is still free stream. The second component is the induced flow of the bound vortex. So the bound vortex is described as a vortex that goes through the quarter chord, okay, of the wing. And the circulation of the vortex is directly proportional to how much lift that particular cross-section gets. Okay? And the third component is the induced flow of the trailing vortex sheet. So these vortices going directly downstream. Okay? Can you just make sure like you actually did this in Unified, right? Yes? Yes? No? No? Okay. So in Unified, when you learn induced drag, like what model did you use for induced drag? Okay, so maybe my Unified knowledge is a few years old, and okay, so maybe let me go through things a little bit more carefully. Okay, so the concept of a vortex is that the whole concept of a potential flow, right, which is the first section of our study, is that the flow can be decomposed, the whole velocity field, not pressure field, velocity field, can be decomposed as a summation, a direct summation of flow induced by vortices. Okay, so here, in this particular model, it's a free stream, just a constant velocity, plus the flow induced by these two vortices. And I'm going to illustrate carefully what is the flow induced by vortices in this lecture. Okay, so let's just think about this as a simple statement for now. Okay, we understand this, and in this lecture, we're going to understand the number 3, and in the next lecture, we're going to understand what is number 2. Okay. And let me just tell you the consequences. First of all, it's useful exactly the same way as the air cylinder model. So it explains lift again through conservation of momentum. It explains induced drag through the conservation of energy. Except for when we look at the flow in the wake of an airplane, explained by these vortices, it is no longer a cylinder. Okay, it is a whole flow distribution. We're going to look carefully in this lecture. Okay, and but by integrating the total momentum in this wake and the total kinetic energy in the wake, we can achieve very similar results as the air cylinder model, but more complex math. Okay, And it is no longer as wrong as the air cylinder model because, okay, it actually explains how the air, like away from the wake, like makes way for the downward flow in the wake, right? It also describes how the air, even inside the cylinder, right, near the airplane is actually moving in non-uniform speed. And it is no longer as unsatisfactory as the air cylinder model. So we're going to look into that in detail. All right. So, okay. So I'm going to skip this and first of all explain what is the induced flow. And the induced flow, we are first going to describe the most simple scenario of the flow induced by a vortex. Okay. And this is a scenario where we have an infinitely long vortex that's aligned with a certain axis. So let's and it doesn't matter which axis it is aligned, right? So but let's say this is aligned with the z-axis. So we have x and y, and a z-axis is going to be pointing out of the screen. Okay. All right. So when you look at the vortex, you use the right-hand side rule. So if the vortex is pointing out of the screen, then the flow goes like that, right? You use the right-hand side rule. All right. So this means a positive z vortex. Okay. So the flow induced by the vortex is the following. It is proportional. It is inverse. So let's say it is inversely proportional to the magnitude of the velocity is inversely proportional to the distance to the vortex. Okay, and the direction of the velocity is perpendicular to the r direction. Right. So these two are very clear. Right. So velocity goes slower and slower as you go away, and the direction perpendicular to the radial direction. All right. Any questions on that? But of course, this is in a radial coordinate, so we have to transform this into a Cartesian coordinate for us to be able to do more manipulations, right? Especially when there are multiple vortices, it's very hard to, there is no unified radial coordinate of centered on two vertices or many vortices. So let's transform this into Cartesian coordinate. Okay, so first of all, what is a vector that's perpendicular to the radial direction? So if this is centered at 0, 0, for example, then the radial coordinate is actually equal to x and y, right? Okay, so if something if something is orthogonal to this radial direction, then the velocity has to be proportional to y and minus x. Right? Do you agree? So that is when I take a dot product between y and minus x with the radial direction, x and y. So I have x times y plus y times minus x. They become 0. Right? So whenever you see something, it's orthogonal to the radial direction, it has to be proportional to y and minus x. Okay? And then next thing is to figure out what is this proportionality constant. Right? It's not a constant in terms of it's uniform in space, but it's constant in terms of it's the same coefficient for both x and y component. All right. So for that, we need to figure out what is the magnitude of this. The magnitude of this is actually exactly r, right? Exactly the magnitude of r, because they're just the switching x and y and putting a different sign. So for the coefficient to make this true, right, the entire magnitude being proportional not r but 1 over r, the proportionality constant has to be 1 over r squared, right? So v now is equal to y minus x which is the divided by x squared plus y squared, which is r squared, right? So this is the whole velocity field of a single infinitely long vortex of some strength. So how do we denote the strength of a vortex? We denote the strength of the vortex by its circulation. So gamma is the circulation. The circulation means if you take a circle, right, that's where the circulation comes from. If you take a circle and integrate the velocity along this circle, that should equal to gamma. Okay, so in our case, if we take this velocity field, right, this velocity field has a magnitude of 1 over r. And if you integrate along the circle with a radius of r, okay, what is the integral? No. I mean, the magnitude is 1 over r. You integrate it along the curve, that is r, right? Remember, the direction is always aligned. So like when you're doing the integration, there is no. I mean, the vector calculus is trivial because the direction is aligned. So what is in this case? What is integral circular over a radius of r, v dot dl? Yes?
2 pi r.
It is, well, the length of dl, if you integrate it, is 2 pi r, right? And the velocity has a magnitude of 1 over r.
2 pi.
It's 2 pi, right? So this velocity field is the velocity field of a vortex, or induced by a vortex of circulation 2 pi. All right. Okay. So in general, if you have a vortex of circulation, maybe not 2 pi, but some gamma, okay, the velocity would be, in general, the velocity would be actually gamma divided by 2 pi times the vector field y minus x divided by x squared plus y squared. Okay, so this is for vortex for a vortex centered around the 0, 0. Okay. Now, like more generally, that's the advantage of a Cartesian coordinate. So for a vortex of circulation, sometimes we also call strength, gamma, centered at x0 and y0, what is the velocity field induced by the vortex? It induces a velocity field that is equal to, okay, let's say v is a function of x and y, that is equal to, let me just write out the two components very carefully. The x component is gamma over 2 pi again, and it's y minus y0 divided by x minus x0 squared plus y minus y0 squared. It is essentially the same as the x component of the origin-centered vortex, but shifted by x0 and y0. So whenever you see x, you replace the x by x minus x0, right? Because that's the relative distance to the center of the vortex. Whenever you see y, you replace it by y minus y0, because that's the relative distance, right, to the center of the vortex. And again, like the y component would be gamma over 2 pi, Now instead of minus x, I have x0 minus x. And again, the denominator is x minus x0 squared plus y minus y0 squared. So that's the most general form of the velocity induced by an infinitely long vortex aligned in the z-axis. All right. Okay. Any questions on this? Okay, so first, right now we're just going to take this as a given, and later we are going to slowly derive where does it come from, right? Why is the velocity field around the so first of all, we are going to see like why are we explaining the flow around the airplanes in terms of vortices, and the second we are going to see like where does this formula come from. Okay, so for now, let's just take this as a given and do some math. So now, the lifting line model basically predicts the flow in the wake as induced by a bunch of trailing vortices. Okay, and first of all, we are going to look at the simple scenario that the trailing vortex, there are just two trailing vortices, one coming from the left wingtip, one come from the right wingtip. So there are two concentrated vortices, but the direction is opposite to each other. Okay, so the previous one we looked at has a direction spinning like this that corresponding to this vortex, and the other vortex spins in exactly the opposite way. So think about this having a strength of gamma, this having a strength of minus gamma. Okay, so let's put a minus sign onto this. Okay, so that's when we look at the formula. So again, let me just pull the formula up into the new page, and it is going to be up for you to work out what is the velocity field. Not everywhere. I don't need you to work out everywhere, but at a select number of locations. Okay, so let's work out what is the velocity field as a vector at the 5 points 1, 2, 3, 4, 5 that forms equilateral triangle. So this is a half span, right? And all of these are half spans. So equilateral triangles around these two vortices. So again, like come up to the blackboards and form groups of two and starts to work out how fast is the velocity. Make it smaller. And here are the chalks. Okay, I will need more. I think I might need to go grab some more chalks. So a second. Yeah. So come start to grab the chalks. I'll get more. Mind just in the classroom to the just the close. Yeah, some chocolate is going to be coming. So
okay.
for those, maybe can we share the chalk so that like right now at least the one team should have one chalk. I mean, if some of you have multiple chalks per team, if you can share them, that'll be great. Yeah, I'll take one. Yeah, thanks. Yeah.
Thank you.
So you still don't have anything? Oh, okay, good.
X minus X naught, so X minus V over zero.
Like for each of these, like one for this one and one for this one.
Yeah, so most of that radius. Why did you plus there? Oh, no, yeah, we did right, yeah. So minus X will always cancel because wait, they should be the same.
So you are calculating the velocity at the first point. What is the XY coordinate of the first point?
We said it was 0, 0.
0, 0.
So
Right.
This would go to 0.
Yeah.
Oh wait, yeah, we forgot. Oh yeah, that's
Yeah. So that helps the calculation quite a lot.
Yeah.
Yeah.
This is our y, so we have no
For the
y.
coordinate system, how do we like define the origin point?
I think the most convenient is to define the origin right at the center.
Right at point.
Yes.
For
right.
all the points?
Yeah, for all the points, right in between these two vortices.
Basically, the main things we can find are just the...
The result shouldn't depend on where you pick the origin, right? But like it's probably more convenient, right at the center. And you're gonna find out for 2, 3, 4, 5, if you do one of them, and if you choose at the center, they are symmetric. Right. And also for the first point, if you choose the center, it's actually 0, 0. X and Y are both 0 for point number 1.
Oh, it's just 0 for number 1.
The coordinates are 0.
Yes.
It doesn't mean the velocity is 0.
Sure. Oh, okay, got it.
Yeah, but I'm saying in relation to this one, like, that is giving us the sense of this.
Since it's 0, 0, it's just like this for x.
And then we need to... Okay. So...
Yeah, if we make point 0, it's like... you have to find this where actually... I believe it's... oh, these are equilateral
Over 3L squared.
This is
Like y squared plus x squared.
Well, I guess it's a negative.
plus
Or y.
This would just be b as this is plus
And then
equilateral.
plus
L squared. This is b is...
oh,
what
happens?
Yeah. Also in the numerator, it's not square root 3. It's square root 3 over 2. Right. If this is your L, This is like square root of, yeah.
Well, no, I know, but I was just it's the same thing, so I might as well just do this.
And the denominator is basically the square of the distance, which is going to be L squared. Oh, thank you so much.
Okay, maybe you should just leave them in here.
Yeah, I'm going to leave it here.
Maybe take some for yourself.
Yeah. Thank you so much. Okay, so for those who need more talks, there are more here now.
No, I thought they had a whiteboard. They never took the chalk down. Isn't that weird? Because people don't use. Oh well. I think they would change it.
No, they didn't. Yeah.
And then for this one, it was a squared plus a squared.
Did you have any eraser by chance?
Yes.
Thank you.
So it's still positive. I mean, if the coordinate will be negative, but these terms oh, right.
Oh, but you did, because you have cancel out the 2. Yeah.
Are we using Y?
Yeah. That's also 3 only to this, right? So we have to sum up this one with it.
2.
Like this. Yeah, so this is like
over X minus oh, it's from here, right? So it's well, we're doing point 2. Yeah.
This is a generalized. You can't have a variable in there.
Yeah, this is so we're doing
This is the same, right?
minus 0, 0.
Maybe if you add them up, it's just the L squared. Yeah. Okay. Good.
Because it's from 2 to
are we doing from here to here?
minus p over 2. So we're doing the x on that's halfway. Bottom part, that's smaller.
Yeah, but
Why is this one like this? So just,
yeah.
said L, 1 to L.
Yeah.
Oh yeah, that's in the middle.
But then in the minus L, that's coming from
I guess, yeah, I kind of
from here to here.
x squared.
Like the top is just the
So L.
yeah.
This is 30. It's not useful.
Yeah, it might be a bit confusing. The x velocity scales with y. The y velocity is needs to have x. Right. Yeah. Good.
Wait, yeah. The x component. Oh, not the y. Wait, that's the y.
Oh, it's not y. It's a 4.
Yeah, the number.
Where we're going. Why not?
Yes. Yeah.
Like we're not putting actual. You don't put x and y. You put because this
You
would
put
be
the actual coordinates.
yeah. So it'd just be it was point 1 would be 0, 0
Yes.
to going into each of the x and y's.
Yes.
And so then yeah, for this you put the coordinates of this minus the displacement of this from this vortex and then this from this vortex.
Yes. Yes.
Okay, so for this example,
For which example? Point 1 or point 2?
point 2.
Okay.
So when we have point 2,
Do you have point 1 now?
yeah, that's 0.
Of 3
That's
b
0.
Oh no, that was just 0, right? So it was just B 0.
That's 0, right?
Do you have contribution from both vortices or just the one of them?
Just this one.
Just this one.
The Y component.
Yeah, so X component is 0, I agree. For Y component, you need to add up the contribution from both vortices.
It'd be 2, right? 2 times.
Yeah, it'll be 2 times. And you are missing a square on the...
Yeah, here I erased it.
Yeah. Okay, good. Yeah, now for point 2?
For point 2, we know the coordinates are relative to this system.
Yeah.
It is in the y direction. It's L away or L up, and so
the square root of 3 over 2L up.
Oh, because this is L.
Yeah, these are flipped. So there's messing notation.
Also, that's the whole string component of that string.
L, right?
Yeah.
Minus
X and Y.
The distance minus the y distance.
Minus, not the Y distance, minus the Y location of the vortex.
And the y location of the vortex is 0.
Yes.
60, yeah, that's 60.
So then we want this component
Over, and then we would have
that's the bigger one. So the cosine,
the x component of the vortex.
Well, the interpretation of the whole denominator is the square of the distance to the center of the vortex, which in this case is what?
The distance from the coordinates from here to the vortex.
Yes, squared.
It's 3 over 4.
Unless I'm tripping,
It's
the denominator.
It's L.
It's L. Yeah. So it's L squared.
Oh, yes.
And then it's x minus.
It's just L squared.
Yeah.
X not.
Yeah, but the other vortex is not. The other vortex. Yeah.
Wait, so why is this L squared?
Because if you look at the formula, right, it's
Maybe I'm getting confused about my coordinates.
delta x squared plus delta y squared, where the delta x and delta y is x minus x center of the vortex, y minus y center of the vortex, which is equal to the square the distance to the vortex.
So like the distance formula, like square root of x squared plus y squared. That's what it means.
Because aren't these just coordinates?
Okay, so how is this L?
Because like this is
L squared.
Originally, we would use like these.
Yeah, it's because we are saying like these are equilateral triangles, right? And the definition of point 2 is L away from the vortex and L away from the origin.
Like that's the entire. It's just like the shift.
So how does that actually work now?
I was just thinking since all our x naughts and y
Yeah.
So L squared would be just square of this. And that's what we were writing before.
But
2
this
is b over. Well, all of them are b over 2 shifted here.
This
and then shifted by b.
are the origin points.
So it'd just be like
X0 and Y0 are the center of the vortex.
That's what I was thinking.
The center of the vortex.
Yeah, so
they're here.
X0 is going to be minus L. Y0 is 0. Yeah.
And these are the point.
Yeah. So if you want to do things precisely, X0 for the left vortex is going to be minus L. Y0 is going to be 0. Okay. And then X for point number 2 is going to be minus half L.
I think what's confusing
And
is
the Y for the point number 2 is going to be square root of 3 over 2L. Okay, so if you plug in all the numbers and do the crunching, you're going to get the L.
Sure.
Yeah, you're going to get L.
The point is what we're calling R.
Yeah. This is just one of those.
Yeah, that's right.
So wait, why not is the point where actually like
Any questions on this side? Yeah.
Do these look reasonable at the very end? At point 1? Like at the in between the two vortices?
Oh yeah, this is correct.
Okay.
And this is what?
That's at 2, 3, 4, and 5, because they all cancel. They have all the same velocity going down, correct? Because they all have the same radius, but the x components all cancel. So then the y components would be the same for each of them.
The x component actually for point 2 doesn't cancel.
Wait,
this is wrong. This is so yeah. So the numerators are correct. The denominator for one of them is not b over 2 squared. So the distance from here to here is b over 2, but the distance from here to here is not b over 2.
Oh wait, we did this point and this point. Oh,
No.
Okay. that makes a lot more sense. Okay, hold on. Shit. Erase all of this.
Yeah. Any questions here?
Oh yeah.
It's really like the positive direction.
No, because we said they were all
Yeah.
Because if we do this for 1, it should be going like down, meaning
Yes.
that its value should be negative. But by this formula, it's positive.
So for the negative one, it's b over 2. And for the other one, it's
Oh.
3 b over
Yeah. I flipped the sign. Yeah. You very good point. Sorry. So I think I had a sign error in the formula, right? So according to this, this is actually a formula for a clockwise rotating vortex, right? Because the x is going to be positive when the x velocity is going to be positive for positive y, right? Which is going to be correct for this one, but opposite for this one. So the correct formula is actually the opposite. We should have y0. Let me just. We should have y0 minus y for the x velocity and x minus x0 for the y velocity. Sorry for that. Yeah. Otherwise, you are going to be calculating a velocity that goes downwards instead of a velocity going upward for the y. Yeah.
That doesn't change anything for this because y is still 0.
Yeah, very good catch.
Although I think this will be negative.
Alright, let's think about it. How the velocity scale would stay.
So, yeah, so we'll try to negative by that real quick.
This one's x minus.
I feel like this one is for might be easier to
Maybe 0 minus.
talking about number 3.
Oh, scale it to b.
Yeah.
And like the coordinates. The what? How the velocity scale with the span of the pressure of the balloon.
Yeah.
I feel like just the coordinates, no? It just changes how far away the coordinates are.
I mean, this is by the question means if you increase b by a factor of 2, how does the velocity increase or decrease?
Oh.
Right. So you already have the formula. B appears in the denominator, right? And the power is 1, so it's 1. It scales